Now that we know how to move and animate characters in Unity, we want to learn how to jump. Let's do it. Today we are going to implement a jump mechanic using Unity's built-in character controller, animations, and the new input system. But jumping can be hard to get just right, so we'll do so trying to replicate the mechanic from one of our favorite video game franchises, Super Mario. My name is Nikki, and this channel is I Heart Game Dev, my channel all about game development. The biggest shout out to all the new backers and supporters over on Patreon for not only your support, but for also helping to choose this video's topic. Let's get started. What can we learn from Mario's jump? Quite a bit, actually. Outside of Mario's jump feeling perfect during gameplay, it consistently reaches the same height every single time as long as the jump button is held down. We can also see that once Mario reaches the apex or max height of the jump, he begins to fall faster. And we know that if we let go of the jump button, it will shorten the duration and height reached for the jump. By slowing down playback, we can see that the animation transition between Mario's idle, walking, and running states to his jumping state is instantaneous. And if we jump consecutively, Mario performs alternate jump types, each with its own animations and trajectories. We have a checklist of what can make a great jump. Let's go through and try to replicate each component that we just defined to make our own jump. By the end of this video, we'll have a jump that looks just like this. Opening Unity, let's recap the previous episode of the series to make sure we're all starting from the same place and have the same fundamental understanding of what we are working with. We have downloaded the Jammo character model featured on the hit YouTube channel Mix and Jam. We also went ahead and both downloaded and retargeted animations from Adobe's Mixamo platform for Jammo to use. Jammo has an animator component to control the transitions between animation states, and a character controller component that we use for movement and collision detection. We've used the new input system to create an input actions asset, and within that we've set up an action map and actions that currently track the player's input for both movement and running. And to actually use all of that, we've programmed the movement, animations, rotation, and gravity for Jammo. Be sure to check out the full tutorial to get the complete walkthrough, or you can grab access to that project file and this episode's complete project file over on Patreon while also supporting the channel. Otherwise, you can sit back and enjoy the video by just watching to see how we implement this version of a jump. Taking a look at our player input action that we created to use the new input system, we'll see the character controls action map. Here, we currently have the movement and run actions, which are how we currently give players control of Jammo. Let's start by creating a new action called Jump, which we will keep as the action button type. In our code, buttons will return Boolean true or false values depending on if the player is pressing the button or not, so we'll be able to use that when programming our jump logic. Next, we'll need to map this to a couple of buttons. Pressing on the plus button next to the action, we'll see the option to add a new binding. When we select this newly generated binding, we can use the binding property to select which button we want our jump to be set to. And using the listen option, we can just press spacebar for the option to be selectable. We can also add another binding, except for the A button or south button, on a controller by following the same process. Great! Let's open up our code and begin to program our jump implementation. Based on the jump action that we just set up in the editor, let's program the jump callback function that will keep track of whether or not either of the assigned jump buttons are pressed. We can do so by first creating a variable that we will use to store the jump button's current value. We'll write the Boolean isJumpPress is equal to false, because by default, the player will not be pressing this button. Next, we'll write two callback functions that will keep our isJumpPress variable updated to the proper value. As a reminder, callback functions are executed when certain events take place and provide context or data for us to use from that event. So we'll want the callback function to be triggered when the button is pressed and when it's released. Now in the previous episode, we also set up callbacks as can be seen here. To properly update our code with the player's input, we set the callbacks to be invoked during the started, performed, and canceled phases of the player's input. What this means is that when a button is first pressed, the started phase is triggered and our callback is run. The performed phase is typically triggered when a player's input has been completed or updated, like an analog stick moving from left to right. And the canceled phase is when that player input has stopped that form of input, like releasing a button. For our jump callback, we'll only need to know when it's initially pressed and when it's released, so we can use started and canceled. We'll write player input.charactercontrols.jump.started, which will map into our player input action, into the character controls action map, select the jump action, and designate that we want to listen for the started phase. We'll then add plus equals, passing in the callback function that we want triggered. We will name that callback onJump, and we can define that function below. But first, we will duplicate this code and replace started with canceled. OnJump will not return any value from the function, so we can write void onJump, which takes context of type inputAction.callbackContext as an argument. As a reminder, inputAction.callbackContext is only available if we import the namespace unityengine.inputSystem, and we have access to the player input only because that's what we titled the input action asset, selected to generate a C# class, and created the instance of it within our code. This was all fully explained last episode. Within the callback, we'll set the isJumpPress value equal to context.readValueAsButton. And just like that, we'll have access to whether the jump button is pressed from within our code. We can test this by also logging the value to the console just to be sure. Awesome. Now we can actually focus on learning how our jump will actually work. As a disclaimer, I am not an expert in physics, so this is going to be my interpretation of some excellent resources that I found when researching for this video. The links will be in the description. Let's start by visualizing a character jumping. How do we actually get them into the air? Well, physics would say that we apply a positive force. At the start of a jump, the velocity y value of the character will immediately bump to a relatively high positive number one time. We can consider that explosive force the initial jump velocity. This point in time will actually be the highest that the velocity y value will reach, because gravity is the constant negative acceleration that is continuously going to be added to the velocity y value. What this means is that over time, the character's upward velocity will slow. The character will reach the apex or highest point of the jump, and then the velocity y value will proceed back to a negative number and bring the character back down to the ground. And that is a jump. Now, what can we actually take from this understanding of jumping? If we graph out the velocity over time, it would be represented by a descending line because our acceleration, gravity, is a constant negative number being added to the velocity. And as just mentioned, the initial starting point of the jump is the highest that the velocity y value will be. If we were to track the character's position from a standstill, because gravity is a constant number, we'll find that the trajectory maps out to be a symmetric curve known as a parabola. Knowing that the arc of the jump is a parabola is incredibly helpful. The properties of a parabola will enable us to actually find the values of variables that we'll need to make our character jump in our code. So what are the variables that we'll need for a jump implementation? We'll use gravity as the constant negative acceleration, initial jump velocity that propels our character into the air, max jump height, which is the maximum height we would want our character to reach if the jump button is held down for the entire time of the jump, and max jump time, which is the longest length of time for the jump possible from a standstill until it reaches the same y position that it started at. And we'll also add isJumping, which will be true or false depending on if the player is actively jumping. Let's go ahead and declare variables for each of these in the scope of the class. Each will be of type float except isJumping, which will be a boolean. And actually, gravity is something we set up in the previous episode, as we'll notice both the gravity variable and another called grounded gravity. This additional grounded gravity variable is used when the character is grounded or touching the ground. When grounded, we switch to the smaller value, making it less likely for the character controller to clip through the floor from too high of a downward velocity. We also have a function called HandleGravity that currently performs this logic, switching between the two. But let's take a second to move it to the bottom of the update function. HandleGravity is called inside of the update function, which means that it's called once per frame. We'll also notice that the character controller's move function is being called inside update function as well. The character controller's isGrounded property is determined by if the character was touching the ground in the last move call, which is why we move it below where move is called. Getting back to the variables that we just declared and our new knowledge of jumping, let's take a look at the formulas we can use to get our desired jump implementation. Let's create a new function titled setupJumpVariables, which we'll call inside of awake. Now, with parabolas, we can calculate gravity using the following formula: -2 times the max height of the jump over the time to the apex of the jump squared. And because we know our jump parabolas are symmetrical, we know that the time to the apex of the jump is 1/2 times the max jump time. Let's declare a new variable, time to apex, which cuts the max jump time in half. But we'll need to know how long in seconds we want this jump to take for the max jump time. Let's set a default of 1/2 second, making the time to the apex 1/4 of a second. We can, of course, modify this value later to speed up or slow down the jump based on the result and our preferences. And we will also need to establish the max jump height value for the top half of this equation. Let's set this variable to a default value of 1. Again, we can modify this if the jump isn't high enough or if it's too high. Now, let's set the gravity variable to our equation. Okay, we have gravity, time, and jump height covered. Of our variables that we need for this jump, we just need to calculate one more: initial jump velocity. We can calculate this using the equation 2 times the max jump height over time to apex. And lucky for us, we already have those values. Awesome, we have what we need to jump, and our variables are calculated properly through science. Now, if you want to understand these equations a little bit more, be sure to check out the GDC talk Math for Game Programmers, Building a Better Jump, presented by Kyle Pittman of Minor Key Games and Gearbox. Kyle does an amazing job elaborating and explaining why this is such a solid approach to jumping. We are ready to jump. Let's write the first iteration of our jump function, HandleJump. Here, we'll check to see if isJumping is false, the character controls isGrounded property is true, and that the isJumpPressed boolean is also true. If these conditions are met, we want to set isJumping to true, and we want to add our initial jump velocity to our velocity. Remembering from last episode that we have the two variables that store our possible velocities, current movement and current run movement, we will want to add this initial jump velocity to the y value of both. And because our handleGravity function continuously applies gravity to both current movement and current run movement, we can count on both velocities always having the same velocity y value. Now, let's invoke HandleJump at the bottom of our update function and enter play mode to see our current results. Success! Our character jumps into the air and falls back down. However, we will notice that we can only jump one time. That's because one of our conditions in the HandleJump function is not being met. isJumping is always set to true after the first call is made, but never set back to false. In our HandleJump function, which is invoked every frame, we could add an else-if conditional statement that checks to see if the isJumpPressed variable is false, the isJumping variable is true, and the character controller's isGrounded property is true. If that's the case, then we should set isJumping back to false. Testing again, we can now see that we are able to jump multiple times. Awesome! There are a couple things that we should be clear about. The isGrounded property can be quite finicky in my personal experience. If the character is touching the ground, but there is no downward velocity, the isGrounded property will be false. Additionally, it's about time we talk about our current implementation of velocity. At this point, we can look at where we set the current movement and current run movement x and z values. These values do not accelerate or decelerate in the current implementation. Instead, they are set directly to constant numbers. So they are fine as is. But with our gravity, we are adding that negative value continuously over time, meaning acceleration, or deceleration because it's a negative value. With our current implementation, we are simply taking the current movement and current run movement velocity, adding gravity, or acceleration, and modifying the position in the character controller's move function. This is known as Euler integration, and is quite simply the easiest implementation that gets the job done. However, Euler integration has a main drawback. Trajectories are inconsistent depending on the frame rate. Now we're talking about very minor differences, but they can be the difference between a player landing or missing a tough jump, and that can be incredibly frustrating from a player's standpoint. And it's unnecessary because we can actually fix this issue quite easily with alternatives. For today, we'll use Velocity Verlet integration to fix the issue. With Velocity Verlet, instead of solely adding the acceleration to the velocity when calculating the new position, instead we store the previous velocity calculate the new velocity in the same manner as Euler integration, and then we add the old and the new velocities together, multiply by 0.5 to average them, and finally multiply by the time step, which is delta time. So the only place that we need to do this with the current implementation is in our handle gravity function when we are applying gravity to both the current movement and current run movement variables. We'll create a previous y velocity variable and set it to the current y velocity value. Then we'll create another variable titled new y velocity, which will be equal to the old one plus acceleration, which in this case is gravity, times time.delta time. And with one final variable titled next velocity, we'll add them together, multiply by 0.5 to average them, and we'll set the current movement and current run movement y values to this new value. We'll notice that we skipped the multiplication by time.delta time here, but that's only because we multiplied the entire current movement and current run movement velocity variables in the controller.move method. One more change that we need before we test is back in our HandleJump function. Now we can use the same velocity Verlet logic to find the average of the previous velocity and our initial jump velocity value. However, that gets a little messy with the grounded gravity value. Instead, for today, we are just going to multiply our initial jump velocity by 0.5, which will assume that our previous y velocity was 0. And just like that, we have a frame rate independent jump that will always reach the same height. Looking back at our checklist of building an awesome jump, the next step is to modify the trajectory and speed up the jump's descent. As mentioned, the math that we've used to create our jump stems from parabolas, or perfectly symmetrical arches. But part of what makes Mario's jump so great is that it doesn't feel particularly floaty, and we can control the jump's length. Let's first modify our jump so that it's no longer symmetrical and it feels a little weightier. Looking at our graph of height over time, we know that up until the apex, we are considered jumping, and our character is rising. But once we meet that peak height of the jump, the character starts descending or falling. This is the point where we want to start increasing gravity. Let's create a new variable called isFalling. Because we know that at the apex, the velocity y value is 0, we know that from that point on, this isFalling variable should be true. If the character is falling, we'll want to increase the gravity. Let's create another variable titled fallMultiplier and set it to a value of 2. This will be used to speed up the fall. The larger this multiplier value, the steeper the second half of the graph will be, and the faster the character will return to the ground. To apply this multiplier, we can create an additional conditional statement checking if we are falling. And then multiply the gravity being added to our velocity variables by the multiplier. Okay, it's a little too quick and falls a little too short. Let's add another quarter of a second and raise the height to 4. Awesome! Our jump is really starting to feel great to use. It would be even better if we could shorten its length if the player releases the jump button. Fortunately, this is fairly straightforward after the changes we just made for falling. The fall multiplier is waiting to be used once the conditions are met. So for isFalling, we'll also check to see if the isJumpPress variable is false. Now, the fall multiplier will be applied the moment the jump button is released and the character will fall back down faster. If we want, we can also apply a clamp to the velocity y value so that it caps out at a specific max speed. If the character falls from a tremendous height in a game, this would be helpful in preventing the character from falling down at an insanely high speed. But this is completely optional. Okay, we'll definitely have noticed that the character's animation is stuck in the same animation state as the movement state Jammo was currently in, be it idle, walk, or run. We are going to want to switch to some jump animation when the jump takes place. If you are new to animation, be sure to check out my tutorial, How to Animate Characters in Unity 3D, Animator Explained, for a better understanding of what's to come next in this tutorial. Taking a look at the Animator component that's currently attached to Jammo, we'll see the animation controller. Double-clicking on this will open the Animator window and display our 3 different animation states that we currently have, idle, walk, and run. Our character will be able to jump in all 3 of these states. Let's create a new animation state by right-clicking, navigating to Create State, and selecting Empty. Then we'll retitle this state Jump. We need a jump animation. While in the future, we're going to learn how to create our own animations in the 3D modeling software, Blender, today we'll head over to Adobe's Mixamo.com and find a few animations for us to use. we'll select the Y bot from the Characters tab, and then search for the following 3 animations: Female Dynamic Pose, Male Dynamic Pose, and Stylish Flip. We'll use the default settings while setting the format to FBX for Unity. Dragging these 3 animations into our animations folder, we'll select all 3 and find the Rig tab in the inspector. Here, we'll select the animation type and switch to humanoid, then press apply. Our Jammo character is currently set to humanoid, meaning we can retarget these animations to work with Jammo. To be sure that these animations were all imported correctly, we'll select each individually and press on the Animation tab. Here, we can verify that they were all properly named. And for the Stylish Flip, we're actually going to want to modify the animation settings. We'll select Bake into Pose for the Root Transform Rotation setting to remove the root movement from the animation. Switch to Original for the Base Upon setting for Root Transform Rotation, and Center of Mass for Root Transform Y and Root Transform Position, and we'll set the Root Transform Y offset to a value of -1 to slightly move the character higher in the animation. Lastly, we want to modify the keyframes of this animation because there are too many unnecessary parts that just don't blend well. We'll want to move the beginning frame to the pose that looks closest to the regular standing position, frame 6, and the last frame to the moment right before the impact with the ground, frame 40. Pressing apply, and this animation is ready to use later in this tutorial. Let's first get one of these animations working with the jump. Back in the Animator, we can select our newly created jump state, and in the inspector, we can find the motion property. Using the circle selector, we can find the female dynamic pose, and we'll begin making transitions to and from the animation state with all 3 of our movement states. We'll be sure to disable has exit time on each transition so that the animations don't need to finish playing to begin the transition to the next animation. And we'll need to create a new Boolean animator parameter, isJumping. For each transition to the jump, we'll want isJumping to be true. And for the transitions back, not only will we want isJumping to be false, but we'll also need to validate that the other parameters match the corresponding animation state. So back to idle, we'll need isRunning and isWalking to be false. Back to walking, isWalking to be true and isRunning to be false. And for running, both will need to be true. Entering play mode, we'll jump and nothing will happen. This is because we will need to set this animator isJumping parameter to be true and false from within our code. We will set it to true from within our HandleJump function because that's when we are guaranteed to start jumping, and false in our HandleGravity function when we are grounded. Because we already have a reference to the animator component from the previous tutorial, we can set the isJumping Boolean value using animator.setBool, passing in the string isJumping and the proper true or false value. However, we'll create 2 new variables in the scope of the class, an integer titled isJumpingHash and a Boolean isJumpAnimating. Within our awake function, we'll set isJumpingHash to animator.stringToHash, passing in isJumping as the argument. And now we can replace the string version of isJumping with isJumpingHash inside of the setBool functions, and only set isJumping to false if it's animating. This offers a slight performance boost. Testing in play mode, and we'll now see our character switch to jumping when the jump button is pressed. We did it! We can make slight modifications to transitions to and from the jump state so that they're more instantaneous like Mario's. We do this by reducing the transition duration. Selecting the transition and opening up the settings dropdown, let's change the transition duration property to 0.1. This will make the dynamic animations created from interpolating between each animation state much faster than before, and ultimately look smoother. Alright, our character will now play a jump animation every time we jump and transition back to the proper movement state when it lands. Take a look at the comparison. It looks great. But now, let's take this to the next level. As mentioned after the analysis of Mario's jump, we may want to create different trajectories on consecutive jumps. To do so, we'll need to calculate 3 different gravity values and 3 different initial jump velocity values. To implement each jump, we are actually going to refactor the code from earlier. What we'll do is create a new integer variable titled JumpCount, and we'll set it to a value of 0. Next, we'll create 2 dictionaries that we'll use to store the 3 initial jump velocities and 3 jump gravities. A dictionary is a way to store specific values behind assigned keys. You need the proper key to see what's on the other side. In our case, our keys will be the integers 1, 2, or 3, which represents which jump the player is currently on. So in our initial jump velocities dictionary, we'll be able to access the first jump's velocity by using 1 as the key. In C#, we need to declare the type of key that we'll be using, and the type of value it will store. So we'll use int and float, and then declare the variable names for each, initial jump velocities and jump gravities. Then we'll assign these to 2 instances of the exact same type of dictionaries. To add keys and values, dictionaries have an add function. We'll calculate the new trajectories and add them to the dictionaries inside of our setup jump variables function. That way, these calculations occur during the awake lifecycle phase. We know the formulas. We need to know how long we want each jump to take and the max height that we want each to reach. Let's say that our first jump remains the same, our second jump adds a value of 2 to the original height and is 25% longer in time. We'll plug these into our equations and assign them to new variables called second jump gravity and second jump initial velocity. Then we'll create a third jump that adds a value of 4 to the original height and is 50% longer. We'll assign these results to variables titled third jump gravity and third jump initial velocity. Next, we'll add 7 lines of code. The first 3 assign the first, second, and third initial jump velocity values to the initial jump velocities dictionary, and the last 4 will assign the jump gravities with the proper 1, 2, or 3 keys, and an additional key of 0 for when jump count resets. So what does this do for us? Well, now all we need to do to change the trajectory of the jump is replace our initial jump velocity with the initial jump velocities dictionary and key in with the current jump value. This is done by placing the variable in brackets next to the dictionary. And we'll do the same in the HandleGravity function where we are currently using the gravity variable. One thing to note is that we need to increment the jump. We would do so in the same HandleJump function if the conditions to jump are met. So we'll add JumpCount plus equals 1. But to reset the value is going to be a little different. Mario appears to have some form of timer that counts down the moment that he lands each jump. If we wait too long, he just does a normal jump again. For this, we're going to try to use what's known as a coroutine. A coroutine is a function that, put simply, is able to pause its execution for a certain amount of time. Let's write this coroutine function, typing IEnumerator jump reset routine, IEnumerator being the return value for coroutines. Next, we'll type in yield return new wait for seconds and pass in a value of 0.5. What this means is that when the coroutine is called, the first thing that will happen is that the function will pause for half a second before continuing to execute the rest of the code. So after that half a second, we can reset the jump count to a value of 0. So in the isJumpAnimating conditional of the HandleGravity function, we'll write start coroutine passing in the invoked jumpResetRoutine function. If this is proper syntax for coroutines. However, what if we don't want to reset the jump count because the jump button was pressed before the half a second countdown? We can actually cancel the coroutine. We'll need to refer to this coroutine specifically, so we can declare a new coroutine variable in the scope of the class titled currentJumpResetRoutine. And we will set this equal to our start coroutine code in HandleGravity. So at the start of the jump conditional, we'll say if the jump count is less than 3 and current jump reset routine is not equal to null, then we'll stop coroutine and pass in current jump reset routine. We only do this if the jump count is less than 3 because we would otherwise want to reset the value restarting the jump sequence anyway. Testing in play mode, and Jammo is now jumping at 3 different heights as long as the jump is pressed within the correct timings. Otherwise, we'll see that it resets. Perfect! Last but not least, we are going to need to modify our animator. We'll go ahead and delete the jump animation state. Right-click and select Create Sub-State Machine. What this does is allow us to more cleanly transition between our jump animations and the 3 movement animations. We'll go ahead and create the same transitions to the jump state machine that are dependent on the isJumping condition being true. Then disable hasExitTime, and this time we'll want to set the transition duration to 0 for a snappier jump. Double-clicking on the jump state machine node will navigate us into that state. Here, the big difference is that we can lead back to the parent state, which has our 3 movement animations. Let's create 4 empty animation states. The first is going to be the router, and it won't even have an animation. This is our default state when entering the jump substate. We'll then set each jump animation to the 3 other empty animation states. Setting up transitions from the router to each jump state will disable has exit time and set the transition duration again to 0. And now we'll need a new parameter that will determine which jump animation to play. We'll create a new integer parameter titled JumpCount. For the second and third jump animations, jump count needs to be equal to 2 or 3 accordingly. For the first, however, we'll want it to be not equal to 2 and not equal to 3. This serves as a default animation in case our jump count ever surpasses 3. Selecting the third animation, where our character flips, we're going to want to modify the playback speed so that the animation can be complete even if the player lets go of the jump button and shortens the jump. Let's try setting it to a value of 1.75 and see how that turns out. Lastly, we'll want to create transitions from each of these 3 jump animations and connect them back to the base layer node. But we will be given the option to select which movement animation state from the base layer we want to transition to. As it turns out, we'll want each of these 3 jump animations to potentially transition to all 3 of the movement states depending on the conditions. So we'll create 9 transitions, 3 per jump state. Disable has exit time, modify the settings, and assign each with its own set of conditions for the transitions to take place. We'll use point 1 again just like before for the transition duration. Like the original jump animation state, is walking and is running will need to be true and is jumping will need to be false to transition to the run state. Is walking will need to be true and is running and is jumping will need to be false to transition to the walking state. And all 3 will need to be false to transition back to the idle state. This offers the cleanest transition directly back to the proper state, rather than just starting at idle and working back to the running state if the character is running. And the very last thing we'll need to do is set the jump count value in our code. We can do so by creating a new hash just like before, jump count hash, and set it inside of the awake function using the string to hash function. In our handle gravity function, we'll check to see if the jump count is equal to 3 when we are grounded. If so, we'll reset to 0 and set that in the animator. And in HandleJump, we'll set the animator immediately after incrementing the jump count. Awesome job! There are definitely changes that can make this better, but this is such a solid starting point for a jump mechanic. Of course, you can modify and refactor however you see fit, but I do hope that this has been a helpful walkthrough of how to make an awesome jump. If you want to help vote on what we'll cover next, be sure to check out the Ultra Supporter and Believer tiers over on the iHeart Game Dev Patreon. And if you want to join an awesome growing community, we would love to have you in the iHeart Game Dev channel Discord. For updates on the next video, feel free to follow me on Twitter. The links will be in the description. But that's all for today. Thank you so much for watching, and I'll see you in the next video.